Okay, so hello everyone. Today I'm going to talk about Bible, not the super, but my last contribution I published in the GECCO conference, which is one of the biggest conferences for evolutionary algorithm. And this MABLE stands for Multi-Action Program through Linear Evolution. So it doesn't really mean anything, and I think it's linear emergence. But anyway, it doesn't really mean anything, we just wanted the thing. And the idea is that we wanted to learn some... Yeah. We wanted to learn some reinforcement learning algorithm with continuous control. And to do that, we used genetic programming. So our methodology was to use basically initial algorithm, which are linear genetic programming and Tangled program graph, which I will cover just after, and to get better results on state-of-the-art benchmark for control, continuous control on reinforcement learning, which is a MuJoCo suite, which we will also see just after. And we reached equal performance on 4 of the 6 environments that we trained on. We reached equal performance with the state-of-the-art for deep reinforcement learning, which is a huge achievement for genetic programming. We will see why just like in the presentation. And for the other features that we achieved thanks to genetic programming, we have interpretability, which is not achievable thanks with deep learning, and also some feature selection. And also we have a complexity that is much lower than deep reinforcement learning. So this is a general contribution. We will cover each of these parts during the presentation. So first, what is the environment we were interested in learning? So we are doing reinforcement learning. So the environment are always things that needed a lot of action to be learned. And the idea here, even if it's really bad, this one, but the idea is to learn how to move for these 5 types, how to move as fast to the right. And here you have a pendulum, even if the camera is not really well axed. But the idea is to like get the pendulum standing. And here you have every time the number of state and action needed to control it. So the number of states is the number of inputs. So for example, for the pendulum, you have 9 inputs that tells you what is the pendulum doing right now. So like the position and velocity of different things. And this is the same for all the environment. Here you have 11 information about the position and velocity of the different part of the body and stuff like that. And after you have the actions, which are the torques that you will apply on the different body. So for the pendulum, it's only going left or right. But for the other, for example, you have 3 torque, 1 that we can't really see. But on the LGP, it's the same thing. You have 6, 1 per body joint on each leg. So you can see that it's scaled with a lot of action when you jump to more complex environment, like the humanoid, which requires 17 action, and it is pretty hard to compute if you have a small model. So for the presentation, we're going to focus on the end because it covers basically what we want to talk about, and which is the result for everything after. So we can simplify the end like this with the different body joint and the different actions that we need to apply. So for the end, we have 8 actions. It's called the end, but it's not actually a end, but we don't really care. Okay, so to conclude, as we said, we have some action and some state or observation. The action are the different torques that we will apply, so 1 per joint. And the observation are some position and velocity information on all the different parts of the body. So normally you can use deep reinforcement learning to learn that, which I'm not really going to cover right now, but it's basically algorithms that use deep learning to learn that are really efficient, that reach really, really high results with actually models that are not that big. It's like 2 layers of 200 neurons, so it's not that big. But for us, we want a smaller thing, and we are going to start with linear genetic programming. So I think most of you here have heard of Tangled program graph. Maybe not of linear genetic programming, but linear genetic programming is what is inside the TPG. We're going to see TPG after, and you will see that basically LGP is the first stone of a TPG. So what is an LGP? It's something with some registers, input, execution, and output. Registers are just vector of values that we initiate to 0 at the initialization. And we have some inputs that our value between like different values. And in our case, the inputs are the observations that we get from the end. So we have a lot of inputs from the end. And after we have the execution. The execution is basically some random instructions that evolve through the GECCO process that will do some different things with the input and the register. For example, here we take the value in the register 2, so which is 0 right now, but anyway, and we multiply it with the value of the input 0. Then we do like a cosinus on this value and stuff like that. And we compute a bunch of instructions that are basically at the initialization completely random. And in the end, we output the values that we stored in the first register just here. So this is normally how a classic LGP works. We just output the first value. In our case, it's not really possible because we have multiple actions to assess, as we said, like we have like 6, 8, 17 for the humanoid. So we can change the LGP by saying, okay, now we are going to output different value, and to that we just output the different value of the registers, which is quite an issue if we scale in the number of actions, because having only like 3 values to output is much simpler than having 8 or 17. So I just realized, because this presentation was for initially built for people that were like pro of genetic evolution and stuff like that, I don't really cover the evolution itself. I cover it a little bit after, but not for linear genetic programming. But basically it evolved through some mutation and some crossover of the base agent and stuff like that. So this LGP with this shape had been tried on the end, and it has been tried in the work of Georgiana Dzar, which was here last week and did a seminar. And it reached efficient, like it was really efficient for small environment, like the hoppers that we saw at the beginning. But when we try to scale to the end, the results are actually much less impactful. And the supposed reason is that you basically have all the reasoning and all the thinking process happening in only this execution that is really, really small, so it's not really learning. And this is why when we saw this at the beginning, we thought, okay, let's use the Tangled program graph instead. So Tangled program graph is something, as I said, that uses LGP as the initial stone to build the model. And it's something that looks like this. I don't really describe more, but you have some vertices here, some edges, and some program. And the main idea is that you always have a root vertices that is connected thanks to different edges to some program. And some programs are again connected to edges that are again connected to program. And at the end, at some point, a program can be connected to what we will call an action program. And you can see the difference is that the program has only one output with one red square, and the action program has multiple ones. What is the idea here? If you've seen already TPG, it wasn't actually exactly like this. Instead of having this action program, it was only a value like 0, 1, 2, etc. The reason for this difference is that before we were assessing only discrete environment, like in the Atari games, you just go to the left, to the right, and stuff like that. Here we have continuous control, so we want to say, okay, we want an action of 0.5 and stuff like that, so we need more complexity for it. So, how does the execution happen? Even if you've already probably seen it, but basically we will execute each program one after another with the same inputs each time, and each program with a single red square will output a different value, and we will follow the path of the program outputting the biggest value. So we follow this path and we reach a new team, and we continue the same process. We execute all the program. We can see that we can execute the same program twice. It doesn't really matter. And after that, we just continue the path, so we reach an action program, and this action program just activates all the action, and we hope it works. So this algorithm is really efficient for subtask division. Like if you have a game like Pac-Man, and we know that in Pac-Man there is a part of the game when you run away from the ghost and a part of the game where you want to chase the ghost. It's really good to do that because you could have a team here that is saying, okay, are we chasing a ghost? Are we running away from a ghost? And we just take 2 different paths, and one path is a specialist for chasing and one path is specialist for running away. But on tasks like MuJoCo, it doesn't really work. And the supposed reason is that here you have basically one single really complex task that is learning how to walk or to jump or to run and stuff like that. And it's still one program that is doing the main task in the end. And we thought, okay, maybe it's still too much complicated. And our biggest issue here is that we have a lot of action to assess. We are not really able to scale with the environment with a lot of action. So we thought, could we keep this idea of TPG of dividing the thinking process, but to divide it at the action level instead of dividing at the whole task level? And this is how we came up with the algorithm Maple, which is something that looks like this, much simpler. And the idea is to keep only a program with only one output, but this output will each access one action. So we basically remove all the TPG part, we only keep that, and we have this program that will access the action 1, no, the action 7, this one for the action 2, etc. So this reached really good results, and we're gonna see a little bit how it evolves. So for that, I have some little cards because I was playing Vacher a lot at the time. So how does it evolve? First, we have the initialization. So we just create a lot of agents. We create a lot of agents. We create a number of edges per agent. Each edge is responsible of one single action. What we realized when doing the research is that having as much edges as action right at the beginning isn't the best choice. Of course, we would say, okay, we have 8 actions, we want 8 edges. This is what will happen with the evolution, but at the beginning, it's not a good thing, probably because there's too much behavior, so it's not really able to learn quite well. And we realized that having the number of actions divided by 2 was having quite good results, like better than only one edge, better than all the edges. So we just keep that number. Probably we could try with a random number and it would work well. Okay, and after we just like randomize all the action, like because at the beginning it's completely random. So once it's done, we do the evolution. So the idea is to take an agent and to try them on the environment and to see what happened, like what are the scores of different agents. And what we will do is that we will just select the best one and we will erase the worst one. So there is a lot of selection algorithm. We're not going to go deep into that. After we have the duplication. For the duplication, we take one agent. So randomly, here we took this one. We take one agent and we just duplicate it, like directly duplicate it. And after we start the real mutation process. First thing is to remove some edges. So we take our new agent and we remove some edges randomly. We just take them out. And after that, we do the opposite. We add some edges. So to add some edges, what we will do is that we will duplicate some edges from other agents. This is basically what is done already in TPG. The mutation process is really inspired from the TPG. So the idea is that we take our agent already existing, we take the exactly same edges, with the only constraint that we don't want to add an edge with the same action as before. So like we can't add this edge because we already had the action 1. We don't want to do the same action twice. After we have a new mutation, which is a switch, to add some diversity in the process. So the idea of the switch is to take some action value and to switch them. So we keep the same program, but we just switch the action assessed. And like the idea is just to improve the diversity and to keep some collectivity in the different programs used. And after we have the classic mutation, which I'm not really going to cover, but basically we do some mutation inside the program. So this is classic mutation for linear algebraic programming, but we didn't really solve mutation for linear algebraic programming. The idea is to take all our execution and to randomly mutate some line, randomly add or remove some line and stuff like that. So we just do it randomly on some programs to add again some diversity. And during this mutation, we can also mutate the action used by a program, always with the constraint that it can only be a new action not already used by the program. Okay, so we do that for a lot of agents. This creates a whole new population, and then we will cycle on these different cards to do it over and over, on which time we should reach some good results. So what happened on the end? First, we have the LGP. Yeah, I think everything happened at the same time. Anyway, first we have the LGP and the end that reaches this result, so you don't really know what it means actually, but this is not really good. Because the score of 1000 is basically the end just standing and not moving, so it's quite easy to achieve. So being at like 1050 is not that great. And you can see that Maple, even if it's still close to TPG, it's actually better, even if the structure is much, much simpler, showing that the fact that we divided the action at the action program really improve the result. And after we have this algorithm, which is called MATPG, which we didn't talk at all. And what is it? So we had the TPG before. This is the same graph for the TPG. We tried to do a hybrid version between the TPG and the Maple, where we replace this action program with full Maple agent. So I'm not going to cover that much because we actually did quite some research in it. Actually, it was the original idea. But it didn't really improve the result compared to Maple. It was in all the cases we tried, it was not better, not worse than the Maple agent. And after we have the comparison with deep reinforcement learning, which on this task is still pretty much better than us, but it happened. And after we have all the tasks that we talked about at the beginning, and on the easiest one, we are really able to reach some really good score. And like you can see here on the Hopper, we're actually better than this one, basically the same, like not significantly different than this one. And after it depends on this one, you are really worse than the LGP, we don't really know why. We need to investigate that still. And yeah, so basically there is mostly the last environment where we are not able to scale, but you can see that one of the state-of-the-art deep reinforcement learning is not learning either. So on average, deep reinforcement learning is still better. However, Maple offers other advantages compared to deep reinforcement learning. The one I'm really going to cover here is interpretability, because at the GECCO conference, people are not really interested into complexity, so much that you can talk about it. But basically, we are much smaller than the deep reinforcement learning. On average, in our last paper, we tried, and it was 100 times faster to run the TPG compared to deep error. So probably here we are even much faster because the model is smaller. So anyway, about interpretability, it's something that Georgia talked about last week, but we don't really talk about it that much, I think, here. So to describe it, I just took a definition from IBM to be sure to have like something that you can trust, because usually interpretability is really something that people debate about. So interpretability is about transparency, allowing users to comprehend the model's architecture and the feature it chooses and how it combines them to deliver prediction. And what we are really interested here is the transparency and also the feature it chooses and how it combines them, the part that is bold. So when we have deep error, we just have a model that is computing a lot of stuff and doing like a lot of multiplication and addition and stuff, and we can't really know what it's doing. We know the architecture, obviously. We know that it uses all the features. We don't really know exactly which features. We know how it combines them, but we don't really can understand. Like we just know. And if we compare with the Maple, we have something that is much closer to a white box model. And the reason for that is that we know exactly what it's doing for each action. And also we have some much smaller program. So if I take the best of the Maple agents that we get on the end, that which the behavior are shown at the beginning, is this one. Just gonna let you see because it's there. So it's still struggling to move sometimes, but it's still able to like. You can clearly see that some programs are doing specific things, like the two legs on the right and the left are really like doing the main behavior. The two other legs are more like controlling the movement and stuff like that. So if we zoom on this agent, we really zoom. We can look at what is inside, and we can see the exact execution that it's doing. And this is a real execution that has evolved through the different generation. So what it's doing is that it's taking some inputs, multiplying them with some different rate, and then doing the subscription, the difference of both. And thanks to that, we can extract an equation which tells us exactly what it's doing. And after, we can have this ugly figure that show exactly what it's doing for each action. So it's not really easy to look at. We don't really want to understand everything right now, like especially like this kind of lines where we don't really understand what it's doing. But the main idea is that first, for the smaller program, we are really able to say what it's doing. So if we represent what it's doing, we can say that this action is the multiplication of the angular velocity of the angle between the bike right links, so the angular velocity of this joint, by the Z orientation of the torso. So the Z orientation, yeah, it is the torso here. So we don't necessarily know why it's doing that, how it evolved like this and stuff like that. We could look at it, but it would take some time. Some people are working on that, obviously. But the main idea here is that first we are really able to know, like we know the future, so we could compute basically all the possible value of this, like the velocity and the torque, and we could say, okay, we know that this action will always be in this kind of range. And also we are able to know exactly what it's doing. So if we know that we have a bug somewhere in like a robot or something, we can know, okay, I know that this bug will not affect or will affect my action because I know exactly what it's doing. And we can do the same for this action. So it's basically the same thing. So the action 4 here is a difference between still this angular velocity, and I think is the X orientation of the torso. So, yeah. So another thing that we kept is feature selection, which is something usually inherent of genetic programming, like it's usually able to select only some feature to train on. And here we kept it, but we did it at the action level. Basically, for each action, we are able to see exactly what features it chooses. And it's not always the same. Some states are really here a lot, like the state 28 is really in a lot of action program, which shows that probably during the evolutions, the same program was exchanged between different parts of the team. But some states are really specific for one action, for example, this one. And what we did at the end also is to see the correlation between all the action and all the state. So it is more some explainability, which is more, explainability is more trying to understand after the training what it's doing, why interpretability is more linear and capacity of a model. But anyway, so the explainability is to measure something. And what we did is that we took our agent, we tested it on 20 episodes of 1,000 steps. So it got us 20,000 data. And we did the correlation between all the states and all the data. And we could do it with deep learning, obviously, but with deep learning, we can only do it with all the state input because we don't know exactly what it uses. While here, we're able to do it at a more local level because we know that this action is using only these 3 states, so we can do it on this level. And we can see that most of the time, it's really one state that is really impactful. So, in summary, I hope I didn't we should all asleep. So we introduced a new algorithm, which is Maple, which is made for environment with multiple continuous action in reinforcement learning for our case, but it could be other tasks. It beat the GP state of the art, and it also had pretty good results against the deep reinforcement learning state of the art. And also it kept the inherent capacity of interpretability of a lot of GP algorithms. Everything is implemented with GECCO, obviously. Everything is open source, everything is on GitHub. Great. And for future works, what we are already working on is to add some crossover in it. Crossover is a way of mutating that is usually used in GP, but not in TPG, because in TPG, like to use crossover, as in real life, you need people that look alike, animals that look alike, like you don't reproduce people of different species. And normally. And when you use TPG, you have agents that are really, really different because one agent is a whole graph, another is a completely different graph, so it doesn't really make sense. Here we have agents that really look alike, so it wouldn't make sense to do some crossover. So we tried that already. Also, we want to improve the diversity because a lot of the time we see that we converge really fast at the beginning, like in only like 100 generations we converge, and after for 1,000 or 2,000 we don't really change. So this shows that basically the same kind of population with probably the same agent evolved, and improving diversity in these agents, so having really different kind of behavior could help to have better results in the end. And after, one thing that we lost in Maple, obviously compared to TPG, is the emergence. So the ability to have like different, like multi-layer graph with some decisions, stuff like that, and we lost it here. So we are trying to think of a way to do it again, but in a different way. Because one thing that is an issue, and we said for TPG, is that we always had at the end one action taking all the action, like one big action taking all the action, and it doesn't really work. And like for the humanoid, we are not able to scale right now. But if we look at the behavior, we can see that the bottom body is doing the right thing, like the legs are moving, but the upper body is doing like nonsense. And maybe it would make sense to have a graph that is able to divide the control flow and say, okay, one part of the graph will do only the leg and one part will do only the upper body. And right now, TPG are not able to create something like this. So the idea would be to think of how to create a graph that looks like this. So thank you very much. And if you have any question, feel free to ask. Thank you.
Yes. Yeah. I have a question on the results in the comparison. So you compared a lot to the reinforcement learning. I get why.
Yeah.
But when I look to the box plot, I don't know where it was. Yeah. Like, why are the advantage compared to the NATPG? Because like sorry if you explain I didn't get it. Because like if I'm looking to the box plot, it looks better much of the time because you have more confidence in your results. So why are they better than the?
Good question. The reason is the complexity, basically.
Okay.
Because Maple, the big advantage is that we have a really, really small model in the end because we have one program per model. While TPG, because it's basically based on the construction of TPG, in the end you always have a graph with like multiple teams assessing multiple Maple agents. Some are not really useful, some are. So even if, especially for the Hopper, we have much more confidence. It's still like it's not significantly different. Well, for this one you could have, but the fact that we have a much bigger graph is actually an issue compared to.
It's a cost.
Yeah.
Okay.
Yeah. Thank you.
Any other question?
Maybe just for comprehension.
Yeah.
When you have as your actions are not on all the agents, and some agents share the same action, how do you make the decision of which for all the actions on which agent you take them and you have
for the here?
No, for the yes for the
yeah.
No, I mismatch. You presented the method with this.
Maybe the MATPG, the one with the graph.
This
No, the map.
No, I think it's a map, or the fact that you have many different manual agents, which manual agent you choose.
Okay. Oh no.
Yes.
Yeah. I'm not used to use it. Yeah, here?
Yes, for instance, you have several agents that propose action one. So which action one do you
Okay, so the idea is that in like here we have individual agents, and each individual agent will be evaluated individually. So we just take this agent and we put it on the task, and it will use only this action. So if it doesn't have an action program for the other action, like for example, it doesn't have action 2, it will just take the action 0, so it will not do anything. And so it will be evaluated individually. And so it won't be on the same, like it won't be a selection between which one is doing the action.
Okay.
If we have questions online, also don't hesitate to just open your microphone and ask your questions.
Let's make sure I take for another question. Because like it's something I'm just wondering, like you say a lot of time random on this card slide. But how the random is like is there some law to determine it? It's like really just random, like uniformly random on the edges, or like some tendency that some bias that you add to the randomness.
No.
That's just randomness.
That's the main thing of evolutionary algorithm, that basically just like everything's random, but we use it in a particular way, but everything is random. Yeah. If you try, actually, it's worse. Like if you try to ponderate and do like, okay, it's worse.
We are worse than that's okay.
Yeah.
This is one of the key things with genetic programming. Every time you have a good idea, it doesn't work.
Very often.
Yeah.
A question about the results on the box plot. Maybe it's not clear for me. There's some outliers for the MATPG.
Yeah.
It's what about maybe it's not clear for me, but this outlier, it's okay for you, or it's better to have maybe less confidence but no outlier? Or?
I don't really know like this.
Okay.
Yeah.
Because in some cases we prefer to have less confidence and no outliers, but in this case, what do you prefer?
Yeah.
It depends maybe on how many numbers you have, maybe it will help for the question. But if you have like
probably
10 days, there is a lot.
Yes, I didn't really explain that, but because the training are really long, we did 10 seats per training, but it's not enough to like it's actually like here it's maybe just we have 2 outliers and
yes,
one.
Sometimes it's very sensitive, so if you have maybe only 2 outliers, it's not okay, or it's depend on the, but it's this is for maybe it's okay for me, but probably here it's okay to have.
Ideally, it would be better to have a small variance and of course a very high score. But I would say that having an outlier way above the box plot is actually good. It means that we can sometimes detect, not all the time, but we can sometimes detect a behavior that is much better than the others. Okay. So in a way, it means that we are able to, this means that we sometimes get stuck in the local minima, which is bad for us. But it means that we can also sometimes, if we launch the training several times, discover some behavior that is actually quite good. So now our job is to try to improve the process to make sure that we always discover these outliers. Okay. But this gives us room for improvement. This tells us that, okay, the algorithm can find these behaviors, it is able to model them, and it is sometimes able to evolve them, which is very good news. Now, we would like to have them, especially if they are above, we would like to have them all the time. And this is something a bit tricky that we are working on to improve the diversity of the exploration and to try to always match these behaviors. So it's not necessarily a bad news for us. It's especially if it's above, it's mostly room for improvement.
Yeah, because probably like when we look at actually, I think I showed the training. You can tell the training that it's really converging really fast to a classic value. And probably, well, actually, I put this wrong example because my body is improving. But like on this one, for example, we are converging like quite fast. And what it's showing is that probably you have like 1 or 2 good agents at the beginning, like right at the beginning, that evolve really fast with a good behavior. And basically everyone will follow because we don't have enough diversity. So it will just duplicate with everyone, do some changes that are maybe not big enough to be different. And so it will just evolve like this. And we can see that most of the time it's evolving really different things. So we took 6 different training from the Walker 2D, and we showed the different behaviors that it evolved in the end. So the TV is not really showing what is happening. But basically all the way of working that are learned are really different. But this is like with 6 different complete populations, 6 different training, and it's not the 6 best agent of a population, because probably it would be something that it's I don't know why some part of the TV is not really good. Like sometimes it evolves things that are close, but most of the time it's completely different. Like this one, I don't know why, but like it's kicking somehow. So yeah.
One of the legs is not working.
Yeah.
Thank you.
No problem. Okay.
We don't have any other question. Then let's thank our speaker again.